Taylor, you're being reductive. Okay. Not all a fidget spinner is. We all know they're highly complex, nuanced phenomena.
No.
Okay. All right, let's go over the basics. This first thing, guys, I'm going to go over like the super duper basics. So you might want to take some notes on this on a separate sheet, or you could, I guess you could, some people in the other class put it on the back of their sheet. It's up to you. But I'm going to go over like, usually I would just jump right into this, but I was like, no, I'm going to go over like, this should hopefully be like super simple stuff that you're like, all right, yeah. Bear with me for 5 minutes. I'm going to go over like what sine, cosine, and tangent are. So triangles, way back in the day, you learned about similar triangles. So for example, here's a really nice one. Just so happens that you can make a right triangle that has side lengths of 5, 12, and 13. Just happens to be a Pythagorean triple. And then let's say this was angle A, this is angle B. You could, the first thing to notice is, well, if I expanded that triangle out, made it say twice as big, just for example, so it was 10, 24, 26, these angles wouldn't change. Does that ring a bell? Mm-hmm. Or if I shrunk it down, so it was 2.5, 6, and 6.5, same thing. These angles would stay the same as the thing shrank or expanded. And so then you'd say, well, okay, then if these angles stay the same, I can make some statement about ratios involved for these angles. So like A, they invented these words, sine, cosine, and tangent. The sine of angle A, who remembers what the sine of angle A would be?
Opposite of adjacent.
Very good. Okay, so there's a mnemonic, SOHCAHTOA. This is one of the good mnemonics because sine, cosine, and tangent are just arbitrary like words that were made up to represent this idea. So a mnemonic in this case is good because it'll help you remember like what the definitions are. So this one says that the sine of an angle is the ratio between its opposite and its hypotenuse. The cosine of an angle is the ratio between the adjacent and the hypotenuse. And the tangent of an angle is the ratio between the opposite and adjacent. And the idea, it all comes back to like similar triangles. If you blew this thing up twice as big, these ratios would still be the same. All the proportions wouldn't change. Okay. Markers running. Okay, so what's the cosine of angle A then?
12 over 13.
Cosine of angle A is 12 over 13. And the tangent of angle A is 5 over 12. Any questions yet? Okay. Now here's the thing, it's all relative though. Like if you ask angle A, hey angle A, who's your opposite side? He's going to say 5. But if you ask angle B, hey angle B, who's your opposite side? He says the 12, right? So what I'm getting at is if you go, okay, what's the sine of angle B though? The sine of angle B is his opposite side divided by the hypotenuse. And these guys would agree, they'd agree on what? They both agree that 13 is the hypotenuse, it's the longest side of the triangle. Oops, be a C there. Cosine of angle B is 5 over 13. And lastly, the tangent of B. So, and it's pretty evident that there's a whole bunch of connections between these things. Like if you make it on one triangle, like for example, the sine of B is the same as the cosine of A. And for example, the tangents are reciprocals of each other. So there's all these kind of things going on that you could think about. So there are three more we got to look at, which is what about the, where's here? There's secant. So the secant you abbreviate as SEC. And I'm just going to generalize this. The secant of an angle is just the reciprocal of the cosine. And then there's a cosecant abbreviated CSC, which is the reciprocal of the sine of your angle. And there's also a cotangent. A lot of vocabulary here, kind of boring. Sorry.
It's also confusing.
What do you, okay, let's
Yeah.
go back.
Cosecant should be the reciprocal of the cosine. Cosecant, cosine, not the other way. It's confusing.
Sounds like your bootstraps are not
It's on the
fully
ACT,
engaged.
and it's like, what?
There is actually some etymological reason for like why does cosecant go with sine, but secant goes with cosine. Again, when we talk about the unit circle, I'll try to remember that. Usually when I try to explain that stuff, everyone just goes, even more so than usual, which is a lot and saying a lot. But it all comes down to like you draw the unit circle and then you can extend the unit circle geometrically and show how there's the secant line. There's a segment that you can call the secant that it makes sense to call it the secant, and there's a line that makes sense to call it the cosecant, and then you can show geometrically how well this has to be the case. So anyway, although then you always think, well, couldn't they have swapped the definition of sine and cosine? Is there anything wrong with that? But anyway, so
They.
they don't. Well, the thing about all math is like no one really like. It's not like single people like discover things, but a lot of it just kind of emerges, kind of like language does. You know, just kind of comes about through the many human connections that are going on all the time. So it just kind of emerges out of that.
Formulas are named after people a lot of the times. It's like if words were like, this person discovered this word.
Yeah, that's true.
It would be hilarious.
What's crazy is so many of the things are named after some famous person, but then you're like, oh, who actually came up with this theorem? Oh, some other guy. Not the one it was named after. Like, oh. Okay. It was like, oh, who came up with L'Hopital's rule? Was it L'Hopital? No, someone else. I'm pretty sure even Euler's number, it wasn't Euler. Euler came up with a whole bunch of stuff. He had discovered a lot of things.
It's actually Einstein.
Alfred Einstein, sorry. Or Alfred Eisenhower, as I discovered last class. That's his true name, Alfred Eisenhower. But anyway, yeah, so like a lot of times they'll be like, well, what happened is something will kind of gain traction is this E. Oh, E comes up over and over. And then after the fact, they go, oh, we should name it after someone. Euler's pretty sweet. And then they dig deeper later and go, oh, it wasn't him. It was someone actually come up with it before him. All right. Where were we here? So,
Cotangent.
yeah, so these are reciprocal. So for example, I can write them out if you guys want, but what's the secant of A? What's the secant of angle A then? 1 over 12 13ths, so 13 twelfths.
Yeah.
I'll write them out. Just if you're a little confused, you might want to write this down and then like review it later just to make sure you understand it. So I'll give you a couple examples. This based on that stuff, the secant of angle A. What's wrong?
There's so many words.
It's 6. There's 6 words.
That feels like a lot.
I don't know how we learned a language.
The secant of angle A. The secant of angle A, it would be the reciprocal of the cosine of A. So you look at the cosine and you reciprocal it. So it'd be 13 twelfths. And then the cosecant of angle A would be the reciprocal of the sine. So you look at what's the sine of angle A, it's 5/13, so this would be 13 fifths. So if you start thinking about it, what kind of numbers, at least at this point, if you're defining this trig stuff in terms of a right triangle, then the sign has to be somewhere between 0 and 1, right? If you think ahead, you go, wait a second, I know that we're going to extend this definition out to include some negative numbers if you're good if you're thinking about that. But for now, we're just focused on the right triangle. Cotangent of A would be the reciprocal of the tangent, so 12 fifths. There's 3 examples for you. I could list out all the B's if you want, but they're the same thing. They're reciprocals. So anyway, guys. So by the way, if you're thinking ahead, if you're like, what's the big picture here? The big picture is you define these words because they tell you about proportions that exist when you're dealing with angles. And then what we're going to do in a few days is say, well, what if, because right now, what kind of numbers, based on this picture, what kind of numbers can you plug in there?
Positive?
Positive. Can I plug in like 100 degrees? Can I make a right triangle with a 100-degree angle? No, you can't.
Anything less than 90 degrees.
Yeah, so you'd think right now, theta's got to be some angle between 0 and 90, not including 0 or 90, right? What we're going to do soon is extend this and say, well, what if I want to turn this into a function that I can plug any number into? Okay. So anyway, if it interests you all, here, what's the cosine of 100 degrees? Suppose you could do that. You can, by the way, you can. The cosine of 100 is 100 degrees. Let me put it 100 degrees. Yeah. The cosine of 100 degrees is negative 0.1736, blah, blah, blah. So think about that. How the heck are you getting a negative, right? How do you get a negative number out of this stuff? So you may or may not already know the answer to that. So. Okay, ready to go over, that's the groundwork. That's the stuff you got to know. It's the basics. It's the definitions, or at least the starting definitions. You ready to move on to the first problem set problem? Okay, sweet. I'm gonna erase. Can I erase? Yay! All right. While I'm erasing, here's a hint. If you want to try to solve number 1 by yourself, can you draw a triangle that captures that first piece of information? So you want to think about what is x? It says sine of x equals 2/3. Okay, so what kind of thing is x? Once you have figured that out, you then try to draw a triangle that reflects that statement. And once you have that drawing, you then go, well, can I figure out the tangent of my angle based on my drawing? Ready, spaghetti? What kind of object is x? It's an angle. So x, now how do we know that? Well, it says the sine of x. Typically, we take sine of an angle. Sine of x is 2/3. Okay, so how do I make my drawing reflect this? Everyone okay with that? Could I have done a 4 and a 6? Yep. Could I have done a 1 and a 2/3? No, sorry, I meant to say a 2/3 and a 1. Sorry. Yep. I could have done any triangle that has this proportion because it could have been 2 million and 3 million if I really wanted to. Of course, 2 and 3 is the simplest. So then now I'm curious about the tangent of my angle. So what piece of info am I missing? The adjacent. So I need to figure out how big this is. I'm going to call it A. Call it any symbol you want, really. Just don't use X. X is already taken. Pythagorean theorem, right? So A squared plus 2 squared equals 3 squared. Gotta know that one, right? Hopefully. Pythagorean theory. Okay, so this is a 4, this is a 9. If I subtract 4 from both sides, I get this. Everyone okay with that? So how big is A? Square root of 5. So Therefore then, the tangent of my angle is opposite over adjacent, so it's 2 over the square root of 5. How do you feel?
Good.
If anyone's wondering, wait a second, are you allowed to have a square root in the bottom of your fraction? The answer is yes, you are. If you, for some reason, prefer not to have a square root in the bottom, you could certainly multiply this by root 5 over root 5 and get 2 root 5 over 5. That number is the same number as this number. If this is context dependent, there might be a context where this is a more useful way of writing the number. All right. Why don't you try number 2? I'll cover 3 with you because 3 could be a stumper, but we'll compare answers in a minute. Are you okay over there?
Mhm.
You're cold? I can close the window. Is it cold out there? Actually, what kind of chilly? No, it's not cold.
Yes.
It's perfect? What's the perfect temperature, Zane? 70? It's definitely not 70 out.
No, I think that's pretty accurate.
You think 70 is the perfect
Yeah.
temperature?
That's because I wear
No.
hoodies all
Well,
the
Zane
time.
said it's perfect out, and then
Six-
he also said that 70 was the perfect temperature.
63.5.
60
I'm more of like a-
degrees, but sunny.
50, I think 50 and sunny.
Yeah, 60 or 50 and sunny.
If the sun's out in full force, 50 feels hot to me. It feels warm at least.
Yeah,
Jeez, the sun's out, I'm not outside.
like this,
But you're not outside? at
this
sunset?
overcast, if it was 60 degrees, would be grand.
Okay. So the setup here, hopefully is fairly straightforward. I gotta say, well, I gotta draw a triangle. I mean, you don't have to make your drawing to scale if you don't really, all I'm saying is it's not the end of the world if you draw and go, oh, like this. That's a little weird looking, but you can still do the calculations. Anyway, tangent of x, so x is my angle. Right? Who's confident in their answer for this? Anyone? Yeah, what'd you get?
That would be root 17.
Root 17. Everyone okay with that? Just in case anyone's confused, we went 4 squared plus 1 squared equals hypotenuse squared. Remember, the hypotenuse is always by itself in the Pythagorean theorem. Always by itself. The two legs, the two shorter legs are added. Their squares are added. And so you get 17 equals 8 squared. Squeak. Okay. And so the answer to this one is, it's asking, what's the secant? Well, if you're still getting adjusted to the whole secant thing, I would just say, we'll start with the cosine. What's the cosine of our angle here? 4 over root 17. So therefore, the secant is just the reciprocal of that, root 17 over 4. Do you feel okay about that?
Yeah.
Nope. Any questions on any of these steps? Anything going on here? Okay. 3 is a little weird, right?
Yes.
3 is basically like a generalization. What you're basically doing on a question like this is saying, like, you're basically making a formula for if I know the cosine of my angle, how do I go directly from the cosine of my angle to the tangent of my angle? Is there some formula that connects those two? That's the big picture of what you're doing here. So as far as setting it up, it's like this. So you say, how do I make a picture that says this? Cosine is happy. You do this. Triangle, where's x go? The angle. It doesn't, it could be this one or this one. I like putting it in the bottom. That makes more sense. Now, how do I do this? Well, maybe that helps. Adjacent over hypotenuse. And we got to make sure that's a critical step there. Once you get that idea, once you kind of wrap your head around how that works, it's fairly smooth sailing from here. One little tricky part we got to watch out for. There's no questions?
Oh, okay, nope, we're good. Yep.
So the way this is written, so you can do the same thing, guys. Just a heads up if something said, for example, oh, the tangent of your angle was 5, you could go 5 and 1, like that. Okay, so anyway, we got to figure out what this is. I'm going to call him A temporarily. And let's set up the Pythagorean theorem. So it's going to be Smiley squared plus the unknown thing squared equals the hypotenuse squared. And who am I solving for again? A. I'm solving for him. So let's move this guy to the other side. Then what? Square root. Don't make the rookie mistake of trying to turn this into 1 minus face. That's not how square roots work, right? You can't distribute the square root over the subtraction. That's just not how it works. So there you go. That must be the size of that third side. So it's asking us for the tangent. With that in mind, what's the tangent of x? This opposite, which is 1 minus smiley face squared over adjacent. So what this does is has basically created a formula that tells you, if you know the cosine of an angle, then if the cosine of the angle is this value, then the tangent of your angle is this formula in terms of that value, which I'm not saying it's the most, it's not like a famous formula because it doesn't tend to be that useful, it doesn't come up that often, but I hope the idea makes sense of the principle. It's clear enough. So, yeah, let's, you guys can have some work time just to, do you guys need another example or you feel like you got it? I'm glad to go over another one if you want. Okay.
We'll let you know.
Thank you.